In this video, we're going to be looking at percentage problems that involve an increase or decrease. So let's look at this example. We're told that a 2% error is acceptable for a machine part to be usable. The part is supposed to be 2.25 inches long. And we want to know what's the range of measurement that are acceptable for this part. So this is what the part should be, but there's a minimum acceptable value, and then there's a maximum acceptable value. And we're told that the way we figure that out is because there's a 2% error. So plus or minus 2%. There's a couple different ways that you can think about this. So the first way is you can think of the percentage formula, percent equals part over whole. You could say, okay, my acceptable error is 2%, so that's my percentage. And we're going to put that in decimal form, so 0.02. The whole would be the part length, 2.25. And then the part would be how far off we can be. So yes, we can be 2% off, but what is that in inches? And in order to solve for this, you would multiply both sides by 2.25. When you do that, this cancels, and we're left with just our value that we can be off by. And 2.25 times 0.02 gives us 0.045 inches. So we can be off by 0.045 inches. However, that's not exactly our answer because we're looking for what is the range of measurement. So we're looking for what is the minimum and what is the maximum. In order to find the minimum, we're going to take the intended part length and we're going to subtract 0.045. And then if we want to find the maximum acceptable part length, we're going to take the intended part length and add on the 2% or 0.045 inches. And when we do that, we get a minimum part length of 2.205 inches and a maximum part length of 2.295 inches. And another way you could report that is like this. Now, there is another way to think about this problem. So rather than figuring out how far off you can be on either side, you could say, well, my minimum acceptable part length is 98% of the intended part length, because we can be 2% off. And then my maximum acceptable part length is 102%, because we can be 2% higher than the intended part length. So a second way to think about this would be percent equals part over whole. And we're still solving for this piece, the top, but now rather than just being the amount we can be off, it is going to be the minimum value or the maximum value. So we are going to multiply 0.98% times the intended part length. And when you do that, you get 2.205 inches. And then for the maximum, we're going to multiply 1.02, 102% in decimal form, times 2.25 inches. And when we do that, we get 2.295 inches. So you see that the range is the same. It's just two slightly different ways to think about the problem. Let's try another example. A contractor ordered 10.5 cubic yards of sand for a job, and that included 5% allowance for waste. And we want to know how much sand was actually needed for the job. So we have our equation, percentage equals part over whole. If 5% was waste, in decimal form that's 0.05. And the whole would be the total amount the contractor ordered, 10.5. So the part is what is going to be the waste. If we rearrange this, we're doing 0.05, the percentage in decimal form, times the total amount ordered. And when you do that calculation, you end up with 0.525 cubic yards. However, this isn't the answer because we figured out this part. We figured out the 5% that was allowed for waste. So in order to figure out how much sand was needed for the job, we need to do 10.5, the total amount sand, minus the amount that was wasted in order to get the amount of sand actually used for the job. Another way to think about this is rather than having the part be how much is wasted, we could think of the top of the fraction as being how much was needed for the job. And then the bottom of the fraction is still the total amount of sand used. But now our percentage changes. So 5% of the sand was wasted. That must mean that 95% of the sand was used for the job. Or in decimal form, that's 0.95. And when we rearrange this, we get 0.95 times 10.05 equals 9.975 yards cubed. So you can see we end up at the same place, but we didn't have to go through this subtraction step that we had to in the first method, because here we had originally solved for how much was wasted, and we wanted to know how much we actually used. So two different methods, two different ways to think about it, but you end up in the same spot. One final example. We're told that steel bars shrink 10% when cooled from furnace temperatures to room temperature. A cooled steel bar is 36 inches long. How long was it when it was formed? So we have the formula percent equals part over whole. And I think it makes sense to say that the whole would be how long it was when it was originally formed. So that's what we don't know. And then the part is what did it shrink to. Now you have to be careful with the percentage because it shrinks by 10%. So that means that this new length is 90% of the old length. It was only 10% shorter. So our percentage here is not 10%, but it's 90%. And in decimal form, that would be 0.9. Now we want to solve for x, but it is on the bottom of the fraction. So what I'm going to do as a first step is I'm just going to multiply both sides by x. That way x cancels here, and over on this side I have 0.9x equals 36. And then second step, I'm going to divide both sides by 0.9. And when I do that, I get x equals 40 inches. So the original length of our bar was 40 inches. And we can check this to see if it makes sense. So if the original length was 40 inches and it shrinks by 10%, well, let's take 10% or 0.1 of 40 inches. That's 4 inches. 40 inches minus 4 inches gives us our final length of 36 inches.